Section 6.3, here we go. Definite integrals and antiderivatives are the topic of the day. One of the big things that we're going to work on is the average value function. You can see that, and then the properties. So let's hit it. I did not have you guys do this. I think we'll skip over that. This was the assignment from the previous lesson. Here are some of those answers. So if you want to check your answers, feel free to move that down. There's some of the answers I got. Just hit pause, and I'm going to keep rolling forward. All right, here we go. This first upper right-hand corner, or upper part of your notes, I guess, has the derivatives of very common functions. And since we just finished that derivative section, we're going to motor through. Rules for definite integrals, you should be very aware of these. We've covered them before, but just point out a few things. We know that if we have an integral from b to a and we want to switch it around and call it a to b, then we take a negative. I know most of the time last year we spoke about how we want this bottom number to be the small number. It doesn't necessarily have to be the smallest. It's just if I want to flip it over, it's going to take a negative then to flip my bounds. The next one talks about a to a. We know that that has zero width, so zero area. Constant multiple, we can pull that multiple out front and call it, it's basically a scalar. Sum and difference, we can break it up into two separate integrals. And the additivity one, this one I want to point out, don't know if we covered this one last year. So if I have a to b and b to c, let's do this, and b, here this one starts at b and finishes at C, there's this link up right here, B to B, that I can come out with one integral that covers from A to C. And if you thought about the area, and I've got those three subdivisions, A, B, and C, maybe my first graph took me through there, and that would be the area from A to B. And my second graph was something like that. Here's the area from B to C. Well, it makes sense then that if I integrated from A to C, I would capture all the area. So I can do addition and simplify it down into one integral. Min and max inequalities are saying if we know the max value of our function f and the min value of the function f on some a to b or a to b integral, then I can say that if I took the minimum height times that width, a to b, that would be less than the actual area of the integral. And that actual area of the integral would also be less than the maximum height times width calculation. So that one kind of makes sense. The domination property says that if f is always bigger than g, so I got f function and I have the g function, f is always greater than g from a to b, then I know that the integral of a to b of f of x would have to be a larger value than the area from a to b of g of x. Because we can clearly see that the area under f is going to be more than the area under g. Easy. But ones to keep in your mind. Now, let's see. Number one, suppose that f and g are continuous functions and that we know from 1 to 2, 1 to 5 of f of x, we have f of x here, and then this one is all about g of x. So this is going to be putting some of those rules into place. From 2 to 2 of g of x, that should be easy, shouldn't it? That is 0 because we have no change in horizontal position. This one, if I want to flip it upside down, of course, we know it takes a negative to do that flip over. And then I've got a match from above, and that would give me an area of -8 instead of +8. The 3 multiplier can come out front. And then I've got 3 integral 1 to 2 f of x dx. And 1 to 2 f of x is negative 4, so I'd have 3 times negative 4, getting us to negative 12. 2 to 5. Here's where I think the work kind of begins. So how are we going to get 2 to 5? I see 1 to 5 and I see 1 to 2. What would happen if I took 1 to 5 and subtracted 1 to 2? I would remove the area then on the 1 to 2, wouldn't I? And this would leave us a 2 to 5 result. So 1 to 5 minus 1 to 2 of f of x dx. I'm really sketching this out. Then quickly, 6 take away negative 4 would equal 10 units. Look for that, what was it called, additivity or something? Yeah, the additivity rule, where you want to work these bounds to achieve the bounds you're after. All right. 1 to 5 of f of x minus g of x. I think we have numbers on both of those. Yep, 6 and 8. So we can basically split these up and think of them individually. And I got to go back. I forgot what the numbers were. 6 and 8. 6 minus 8 leaves us negative 2. On this next one, yeah, I would just think of this as 1 to 5. And the 4 is a multiplier just of f, so that could come out front. But it couldn't come out front until I made separate integrals for each of these functions, because g does not have a multiplier of negative 4, just f. So this would be 5 times 6 minus the 8 from above. So 30 minus 8, 22. The average mean value, did that skip a screen? There we go. Average mean value. If f is integrable on the closed interval a to b, its average mean value on a to b is the average of f, and we come in with a 1 over b minus a. If we think about what this area is doing, let's put this in a different color. Let's say we have some function. Here's our f function from a to b. Then I come up with some big sum number, right? I get the sum of the area. And if I want to find the average of it, I am going to take and divide by the width. And what that basically gives me is an average height that, maybe I do that just a little bit high. Oops. Maybe something down there. What I'm trying to do is balance out the area from above the region and balance it with the area below that region. So this would be considered the average value of the function, that height, where I get the same area if I took and multiplied b minus a times this average height, then I would get the exact area under f of x. So that is an average value function. You can kind of see that picture down below. So the average value of square root of x over the interval 0 to 2 is, well, let's set it up. We know that our a and b are there. So from 0 to 2 of x to the 1/2 dx. And I want to make it an average value, so I'm going to multiply by 1 over b minus a. And that's going to get me my average value. And let's integrate, so we'd have a 1/2. The integral would look like x raised to the 3/2. Remember how we add a power. So I'm adding 2 over 2. That gets me to 3 over 2 multiplied by the reciprocal. And I'd have 2/3 x to the 3/2 as my integral. And I want to evaluate it. from 0 to 2. So we need to put 2 in and 0 in. What I can do is I can bring the multiplier out front if I want, just to make the evaluation of x to the 3 halves a bit easier, less cumbersome. So I'm going to end up with 1/3 out front. And now putting 2 in, I'm going to have 2 to the 3 halves minus, put in 0, minus 0. You know, don't assume that it's always going to zero out. You can get fooled sometimes on that. So be diligent and just carry it through. This looks like it's going to be the square root of 2 cubed. And that is not an answer. But I do know that my power exceeds the index. So I can reduce this down and bring out a 2. And that would leave me a single 2. Because I could break this into 2 squared times 2 to the first. The square root of 2 squared is 2. 2 to the first has to remain. So how about a 2/3 square root 2 right there? Mean value or average, what's the average value of y equals on the interval 0 to 2? Okay, so they talk about the average value. I can do that. The average value will equal 1 over b minus a, so 1 over 2 minus 0. If you want to just put 2, that's fine with me. X squared square root x cubed plus 1. This looks like a doozy to integrate. And we haven't done much integration yet this year, so I don't know if you remember from last year how to proceed on this one. What we want to do is set up a u sub. I'm trying to decide where I'm going to put my u sub information. I think it's going to go right over here. So u sub is the case because I can't distribute the x squared through and get a polynomial with that square root. So my next best step, and I see I've got an x cubed and an x squared. So the derivative of x cubed is going to give me something in terms of x squared. That's the perfect setup for u sub. So let's let our u equal x cubed plus 1. Then its derivative with respect to x. So I'd have du dx multiplied by dx, and it'll come up to the other side. And I'll have 3x squared. And then I look over here. I don't have 3x squared. What I have is x squared, so I'm going to divide by 3 on both sides. So I get 1/3 du is equal to x squared dx. Perfect. So my u sub is all set up. I'm also going to change my bounds. Since it's a definite integral, these bounds are x values, aren't they? And I want to switch them up to u values. So when x is 0, this is our conversion. It tells us how u and x are related. Let's see, we'd have u equals 0 cubed plus 1. So u is 1. When x is 2, u is 2 cubed plus 1. We get 9. All right, I think we're ready to roll. We have the 1 over 2. The scalar is unaffected by all this bound changing stuff. And I'm now from a 1 to 9 because 0 converted to 1 and 2 converted to 9. My x squared dx, this and this, converts to a 1/3 du. And then this portion right here is our u. We said let u equal x cubed plus 1. So we get u to the 1/2. So I know with the scalar, I can move it out front and get 1/6 integral 1 to 9 of u to the 1/2 du. Power rule takes into effect for this nice little integral. So I have a 1/6. U to the 1/2 becomes a u to the 3/2. Dividing by 3/2, like multiplying by 2/3 on the bounds 1 to 9. 2, what do we get? 2/6 is 1/3, so I'd have 1/3 times 1/3. This becomes 1/9. I just pushed these two together. And now I'm going to evaluate, throwing 9 in, 9 to the 3 halves, minus 1 to the 3 halves, obviously 1. And then, let's see, 9 to the 3 halves means the square root of 9, got to take and cube it. Square root of 9 is 3. 3 cubed is 27. 27 minus 1 is what's inside our brackets. And I'm going to get 26 over 9. Was this a multiple choice? 26 over 9. Woohoo! All right. That was a big problem and took a lot of the skills that we learned last year. Walk back through it if you need to. Hit pause, rewind it, go back over it. Use the nit function to find the average value of the function on the interval. At what point in the interval does the function assume its average value? Okay, is this the last thing we have? Nearly the last. Okay. We're going to use the nit function. That stands for numerical integration. In other words, we're going to use the integral function on your calculator. So let me hit pause if I can. Maybe I can't. I don't think I can get to it, guys. All right, you get your calculators out. You are going to set this up just like always. Average value will equal b minus a, so 1 over 3, integral 0 to 3 of negative x squared over 2 dx. That looks messy, and I am going to clean that up. The negative is going to come out front. I am going to have negative 1/3. The 1/2 is coming out front. Integral 0 to 3 of x squared dx. So this will be negative 1/6 integral 0 to 3 of x squared dx. Doing that, now this is what I want to put in my calculator. So let's go to the calculator and get it rolling. Don't know if that would shut it off. So you guys are going to watch me while I open up the calculator. Sorry about that. Should have had that open starting with. It won't take too long. So you get your calculator, get it keyed in, and then let's talk about, I want to talk about the last part, how we get the value at which it's occurring. Okay, perfect. I need to view and put it so that it stays in the front of my screen. I'm going to hit clear, drop down and hit clear, and back over. So, in equation 1, no, not there, I don't. I want to go home. And I want to have negative 1 divided by 6 of the integral. Remember, integrals, you can do alpha, window, option 4. And our bounds are 0 to 3. Oops, where did it go? Yeah, I'm sorry, I'm using arrows on my keyboard and that doesn't always work for the calculator. Next, I need the arrow to the right. Now, x squared. So x squared, sorry guys, and then x. Woo! Enter. I get negative 1.5. Oh, that was a nice answer, wasn't it? Negative 1.5 is our average value. Now, the second part says, at what point does the interval assume this position? So this is like an f of c. You know what, I'm going to do capital F to show it's the antiderivative. And I want to take and set it equal to where this function, it's not writing, that function takes on the value of negative 1.5. So negative 1.5 is equal to negative x squared over 2. Multiply up, I get negative 3 equals negative x squared. This is just as easy to do on my hand. So it looks like x equals plus or minus the square root of 3. But we have to remember we're on a restricted domain. And so on 0 to 3 means that x would take on the value of square root of 3. That's where the x value leads to the height of negative 1.5. I want to show you a visual of what we just calculated. So we came in with the average height, f of c. We said this had a negative 1.5. Obviously, the picture doesn't quite correlate to what we were doing, but it's the same idea here. That's the average height. What we did by setting negative 1.5 equal to negative x squared over 2, we were able to find the x value that leads to that height. And we found our x value to be the square root of 3. Okay? So just wanted to give you that visual of what we solved there. This one is kind of tricky. Find the average value of the function on the interval without integrating. We want to use geometry of the region between the graph and the x-axis. So here's our function that is in blue. And then we want, from negative 1 to 1, we want to find, what did they say, the average value. So average value is equal to 1 over b minus a, integral a to b, of the integral 1 minus square root 1 minus t squared dx. Yeah, it would be lovely to have the calculator do this for us, wouldn't it? 1 over 2 integral negative 1 to 1 of 1 minus square root 1 minus t squared dt. But the shapes that we're seeing are not bad shapes. I see circles. If I were to compute this inside piece, it would be half of a circle, a semicircle. But that's not the region that we want to represent our integral. The integral space is between the curve and the x-axis. So the area that we're trying to compute is this region right in here from negative 1 to 1. And then we won't forget to do the average value of it. So I think what I'm going to envision is this outer rectangle that is what? Negative 1. It's 2 units wide by 1 unit high. So my rectangle space is 2 units wide by 1 unit high, giving me an area of 2. The semicircle is normally a circle area is pi r squared. We have a semicircle, so we have a 1/2 pi r squared. The center of our circle would be there, and we can see that the radius is 1 on the circle. So we have a 1/2 pi 1 squared. So I have a pi over 2. Sorry, my lights just went out. I had a pi over 2 going on here. So now to find the blue area, I'm going to take rectangle minus semicircle. That did not look like much, did it? Semicircle. And that's going to leave me 2 minus pi over 2 as the region in blue. Sweet. Now, sorry, I moved that. That's the answer to the integral. And then we aren't quite done with this problem because we need to say the average value is equal to 1/2 of the integral. And the integral was a 2 minus pi over 2. And you can distribute that if you wish. But there's the answer. All right. What do we have on the bottom? Find, the derivative of the antiderivative. We did these last year, and the next lesson picks up on this too. The derivative of the antiderivative. These are inverse functions, so they are actually really very easy to do. I do not need to take the time to find the antiderivative and then take the derivative again, because it would bring me back to this. Only the one thing you need to remember is that x works its way in. So this becomes the function evaluated at x times the chain rule derivative of the bound. And that derivative of the bound is going to be 1. So this would turn out to be just f of x. Okay. All right. That concludes it. You guys look for the homework it won't be on my math lab. I will find new homework for you. Have a great day.